Hey developers! Welcome back to Vidaysketara YouTube channel, your dedicated space to learn real-world software engineering concepts in the most practical and crystal clear way. Today, we are going to dive deep into one of the most powerful pillars of solid principles, the Dependency Inversion Principle. If you want to become a professional developer, write clean architecture, build scalable applications, and design enterprise-level systems, then this principle is absolutely essential for you. Let's start with a question. Have you ever worked on a project where changing something small in one place suddenly broke multiple areas of the application? Or have you seen code where one class is directly dependent on another class, and because of these tight connections, even a small modification becomes risky? Maybe you wanted to switch databases, change a payment gateway, replace an email service, or update a logging library. But as soon as you tried to change it, everything started crashing. If you faced these situations, then what you actually experienced was the absence of dependency inversion. Dependency inversion is a principle that helps us break tight coupling between software modules. In simple words, it helps us design software where high-level modules do not directly depend on low-level modules. Instead, both of them depend on abstractions like interfaces or abstract classes. The principle also says that abstractions should not depend on details, but details should depend on abstractions. This may sound slightly technical at first, but don't worry. By the end of this video, you'll not only understand it clearly, but you'll also be able to apply it confidently in your real projects. Let's break it down in the simplest way possible. In every project, we have high-level modules and low-level modules. High-level modules usually contain our business logic, the most important part of the application. Low-level modules handle specific operational tasks like database communication, payment gateway integration, notification services, logging, API calls, etc. Normally, in traditional poor design, we directly connect high-level modules with low-level modules. For example, your business logic might directly call a specific database class or directly use a Razorpay class for payment. Initially, this may look simple, but the real problem appears when requirements change. Imagine this scenario. Your business layer is directly connected to SQL Server. After a few months, your client says, "We want to migrate to MongoDB." Now what happens? You are forced to touch your business logic, rewrite code, modify multiple places, risk introducing bugs, and spend unnecessary effort. This becomes even worse when many modules depend on that same database. The same problem happens when you want to replace a payment gateway, logging library, email provider, SMS service, cloud storage, or any other dependency. This kind of coding style locks your system, restricts flexibility, and creates long-term pain. That is why dependency inversion exists. It protects high-level business logic from frequent changes. Instead of directly connecting to low-level concrete classes, we introduce an abstraction layer. This abstraction is usually an interface or an abstract class. The high-level module depends on that abstraction, and the low-level module implements it. Now the magic happens. Your business logic no longer cares which implementation is behind it. Whether you use SQL, MongoDB, Oracle, Razorpay, Stripe, PayPal, or any other system, the business logic remains untouched. Only implementation changes. That's the power of dependency inversion. Let's understand this using a real-life analogy. Think about electrical appliances in your home, your fan, TV, refrigerator, washing machine. None of them are directly hardwired to electricity. Instead, they are designed to connect using a standard plug. The wall socket acts as a standard interface. Electricity providers can change, wiring may change, infrastructure may upgrade, but your appliances still work because they depend on the interface, not the internal wiring system. This is exactly what dependency inversion does in software architecture. It creates a stable contract that both high-level and low-level modules follow. Now let's relate this to programming. Suppose you have a payment service used in your application. A beginner developer might directly write code like payment service depends on RazorPay class. This works initially, but now suppose your client says, "We want Stripe." Suddenly you must go into business logic and change everything. But a professional developer creates an abstraction first, like iPayment Gateway. RazorPay implements it, Stripe implements it, and any future payment system can also implement it. Now payment service depends only on iPayment Gateway. Now payment service depends only on iPayment Gateway. Tomorrow, if you want to change RazorPay to Stripe, you don't even touch payment service. You only swap the implementation. This is dependency inversion in action. This principle is deeply connected to modern software engineering. Frameworks like ASP.NET Core, Spring Boot, Angular, Nest.js, Node.js architectures, and enterprise systems completely rely on dependency inversion. The reason is simple. Professional software development is not about just writing working code. It's about writing maintainable, scalable, testable, and future-proof code. Projects live for years. Requirements change regularly. Technology upgrades continuously. Without DIP, your project becomes rigid and fragile. Another major advantage of dependency inversion is testability. When your classes depend directly on concrete implementations, unit testing becomes a nightmare. You can't easily mock dependencies. You often end up depending on real database connections or real APIs during tests, which is slow and risky. But when you depend on interfaces, testing becomes super easy. You can create mock implementations, inject fake services, simulate behaviors, and test your business logic independently. That's why every professional testing framework and dependency injection container is designed with this principle in mind. Another important thing to understand is that dependency inversion is not just a coding pattern, it's a design mindset. It forces you to think in a structured, layered, and decoupled way. When you start designing your system, don't think about implementations first. Think about behavior, think about contracts, think about what your system needs to do, not how it will do it initially. Once you define clear abstractions, implementations can change any time without affecting the main system. This is the foundation of clean architecture, onion architecture, hexagonal architecture, and many enterprise patterns. Now let's talk about the impact of dependency inversion in real projects. When applied correctly, it significantly reduces code complexity. You no longer fear changing things. You don't break existing modules when enhancing features. Teams can work independently. One team can handle business logic while another team works on infrastructure because both meet at the abstraction level. This also improves collaboration, modularity, reusability, and long-term stability of the software. But remember, dependency. Inversion must be applied carefully. Don't create unnecessary abstractions just for the sake of it. Use it where dependencies genuinely exist, especially in places where change is expected or when you deal with external systems. The goal is to keep your core system stable while allowing implementations to evolve freely. So to conclude, always remember this simple understanding. Never let your important business logic depend directly on concrete classes. Let both business logic and implementations depend on abstractions. When you design systems with dependency inversion, your applications become cleaner, smarter, flexible, maintainable, and truly professional. If you found this explanation helpful and easy to understand, make sure to like the video, share it with your developer friends, and subscribe to Vidaysketara YouTube channel for more powerful, real-world software engineering content. This is your guide to becoming a smarter, more confident, and industry-ready developer. Thanks for watching, and see you in the next session. Hey developers, welcome back to the channel. In today's session, we are going to understand one of the most powerful concepts in professional software design, the Dependency Inversion Principle. And instead of just learning definitions, we are going to understand it through clear, real-world examples that you actually experience every single day in modern applications. Let's start with something very familiar. Payment systems. Think about popular e-commerce platforms like Amazon, Flipkart, or any online shopping website. These platforms support a wide variety of payment experiences, such as credit and debit card payments, UPI payments, wallet transactions, EMI or installment payments, and of course, refund processing. Now, imagine for a moment that the main business logic of this e-commerce platform directly depends on a specific payment provider like Razorpay, Stripe, or PayPal. That means the business code is tightly connected to a specific payment class. Now, what happens if one day the company decides to replace Razorpay with Stripe? Or maybe they want to introduce PayPal support? Or they want to modify how EMI processing works. Every time such a change happens, developers are forced to modify the business logic again and again. This creates dependency chains, increases risk, introduces bugs, and makes the application hard to maintain, hard to scale, and difficult to test. This situation clearly violates the dependency inversion principle, because here the high-level business layer directly depends on the low-level payment implementation. So what is the correct approach? Dependency inversion principle says that high-level modules should not depend on low-level modules. Both should depend on abstractions. And also, abstractions should not depend on details, but details should depend on abstractions. That simply means your business logic should not directly depend on Razorpay, Stripe, or any specific service. Instead, both the business layer and the payment services should depend on a common abstraction. So instead of directly connecting payment service with Razorpay or Stripe, we introduce an abstraction layer, something like an iPayment Gateway interface. Now Razorpay implements iPayment Gateway. Stripe implements iPayment Gateway. PayPal implements iPayment Gateway. Any future payment provider can also implement it. Now your business layer only talks to the iPayment Gateway abstraction, not the actual payment provider. So tomorrow, if you want to switch from Razorpay to Stripe, or if you want to add PayPal, you don't need to touch the business logic at all. You simply plug in a new implementation. That is the beauty and power of dependency inversion. It brings flexibility, maintainability, and future readiness to your software. Let's move to another real-world example: notification systems. Think about applications that send notifications every day, such as email alerts, SMS messages, WhatsApp notifications, or push notifications. In a poor design, the main system directly depends on email service, SMS service, or push notification service. This means the business logic is directly tied to specific implementations. Now, if the organization decides to integrate a new notification channel or replace an existing provider, once again, Developers are forced to modify the business layer, which is risky and inefficient. But when we apply the dependency inversion principle, the design completely changes. Instead of depending on these specific services, we create an abstraction like iNotification service. Now email service implements it, SMS service implements it, push service implements it, and any future notification service can also implement it. The business logic simply depends on iNotification service, the abstraction, so we can easily add new services, replace existing ones, and modify implementations without disturbing the core system. The design becomes clean, scalable, modular, and extremely testable. To understand the thinking behind dependency inversion even better, imagine a conceptual scenario. Instead of designing systems that depend on concrete objects directly like sparrow, penguin, or ostrich, we design them based on behavior abstractions. We focus on what the system needs to do rather than who specifically does it. We say, I need flying behavior, I need swimming behavior, or I need walking behavior. High-level modules depend on these behavior abstractions, and different objects simply implement them as needed. This mindset keeps your system stable even when implementations change. So what does dependency inversion really mean in simple language? It means never make your important business logic depend directly on concrete classes, libraries, or external technologies. Instead, introduce an abstraction layer using interfaces or abstract classes. Make your business logic depend on them. Let concrete implementations plug into it. When we do that, we separate what the system wants to do from how it is actually done. And that makes our applications incredibly flexible and powerful. This principle is not just theoretical. It is deeply used in real-world frameworks and enterprise systems. Modern frameworks like ASP.NET Core, Spring Boot, Angular, Nest.js, and many microservices architectures heavily rely on dependency inversion. Clean architecture, onion architecture, and hexagonal architecture are all strongly based on this principle. The reason is simple. Dependency. Inversion keeps your core system safe, while letting implementation details change whenever necessary. Another massive benefit of dependency inversion is testing. When your code depends directly on real implementations, unit testing becomes extremely difficult. You may need real databases, real APIs, and real services just to test simple logic. But when your system depends on abstractions, you can simply inject mock implementations during testing. This makes unit testing faster, safer, and more reliable. So, in conclusion, dependency inversion principle is not just about writing code. It is about writing professional, future-proof software. It helps you build applications that are loosely coupled, easy to maintain, highly scalable, and extremely testable. It ensures that your high-level business logic remains protected while low-level implementations can easily evolve with time. So always remember, don't lock your system to a single implementation. Design for abstraction. Let your business logic depend on stable interfaces. Let implementations change freely without disturbing the core system. That is the real strength of the dependency inversion principle. In banking, finance, and government systems, business policies and tax rules change very frequently. New tax slabs get introduced, GST rules are modified, income tax policies change every year, interest calculation policies evolve, and regulatory rules keep getting updated. If our software is directly dependent on concrete tax calculation classes or specific rule implementations, every small regulation update forces us to modify core business logic again and again. This not only increases development effort, but also increases the risk of bugs, breaking functionality, and compliance issues. This is exactly where the dependency inversion principle becomes incredibly important. The dependency inversion principle says that high-level modules, which contain important business logic, should not directly depend on low-level modules, which perform specific tasks. Instead, both should depend on abstractions. It also states that abstractions should not depend on details, but details should depend on abstractions. In simple terms, your core banking or government application logic should not directly depend on a particular tax calculation class, interest formula, or policy engine. Instead, it should depend on an abstraction, such as an interface or abstract class, that represents the behavior, not the implementation. Let's imagine a banking system that calculates tax on financial transactions like deposits, withdrawals, international transfers, and corporate transactions. In a poorly designed system, the main transaction processing module directly depends on specific tax calculator classes like GST Calculator 2023, VAT Calculator, or Corporate Tax Calculator. This may initially look simple, but the problem begins when regulations change. For example, next financial year, government introduces a new GST structure, modifies VAT rules, or changes corporate tax calculations. In such a case, developers must again modify the transaction processing logic. This is risky because the business logic is critical and highly sensitive. One wrong change can lead to financial loss, legal penalties, or audit failures. This is a clear violation of the dependency inversion principle, because the high-level business module is tightly coupled with low-level tax rule implementations. The system becomes rigid, fragile, and extremely difficult to maintain. Now let's see how dependency inversion solves this beautifully. Instead of directly binding business logic to concrete tax rule classes, we introduce an abstraction such as ITAXCALCULATOR or ITAXPOLICY. This abstraction simply defines the contract, how tax should be calculated, without specifying how exactly it is implemented. Now, different tax rule implementations can be plugged into this abstraction. For example, GST Calculator implements iTax Calculator, VAT Calculator implements iTax Calculator, and Corporate Tax Calculator implements iTax Calculator. The business logic does not know which tax rule class is being used. It only depends on iTax Calculator. Now imagine a real-world scenario. Government updates GST rules next year. Instead of touching transaction processing logic, we simply create a new implementation like GST Calculator 2025 that also implements iTax Calculator. We replace the old module with the new one, and the business logic stays untouched. No risk, no heavy rewriting, no chance of disturbing critical systems. This makes the application future-proof, stable, compliant, and easy to maintain. Another powerful real-world scenario is government policy systems. Government portals, such as income tax systems, subsidy distribution platforms, pension systems, and social welfare systems, constantly deal with changing rules. Age eligibility rules change, benefit percentages change, new schemes are introduced, and existing ones expire. If the main system is directly tied to concrete policy logic, every policy update requires rewriting the business system. This increases cost, risk, and implementation delays. But with dependency inversion, we build a policy abstraction like iPolicy Rule or iBenefits Calculator. The system depends only on this abstraction. Different policies like old pension policy, new pension policy, subsidy policy, 2024, income tax policy, 2025. All implement that abstraction. When government introduces a new rule, we simply plug in a new policy implementation instead of rewriting business applications. The system remains stable and adaptable. Finance systems benefit massively from dependency inversion, especially in areas like loan interest calculation, EMI schedules, credit scoring logic, fraud detection rules, and compliance validation. Interest calculation formulas change. EMI regulations change. Banking compliance rules are updated based on RBI or central bank policies. If core loan processing or transaction systems are tied directly to specific rule classes, every update forces deep, risky code changes. Instead, we define abstractions like I-interest calculator, I-compliance rule, I-credit score evaluator, etc. Business modules depend only on these abstractions. Implementations such as RBI Interest Rule 2024, Central Bank Rule 2025, or New Credit Policy Calculator can evolve independently without disturbing business layers. This makes enterprise finance applications extremely robust and regulatory friendly. Another major benefit of dependency inversion in government and finance systems is testing and auditing. These systems require strict testing, legal validation, security approval, and audit compliance. When your code depends directly on real implementations, testing becomes complicated because rules are hard-coded into business layers. But when everything is abstracted, auditors and testers can easily validate separate implementations of rules without affecting business systems. Mock implementations can be used for simulation and verification. This builds trust and ensures accuracy. Dependency inversion also supports scalable architecture. Many government and banking systems operate for decades. Rules change continuously, but systems survive only when they are architected for change. DIP ensures longevity. Instead of rewriting the entire application every time policies are updated, we simply update implementations. This protects investment, reduces cost, and increases system reliability. So in simple words, the dependency inversion principle in banking, finance, and government systems protects your business logic from changing policies. It allows systems to adapt without breaking. It ensures compliance changes do not destroy system stability. It helps developers update rules safely, and it helps organizations respond to legal changes quickly. To summarize, do not directly tie your banking or government business logic with tax classes, interest classes, or policy rule classes. Instead, depend on abstractions like ITAXCALCULATOR, IPOLICYRULE, IINTERESTCALCULATOR, and let the actual implementation depend on those abstractions. This keeps your application flexible, maintainable, scalable, testable, and future-ready. That is the true power of the dependency inversion principle in real-world financial and government systems. The dependency inversion principle is one of the most powerful concepts in software architecture because it changes the way we design systems from rigid, tightly coupled structures into flexible, scalable, and future-ready architectures. One of the biggest advantages of this principle is that it reduces tight coupling between modules. In traditional systems, high-level business logic directly depends on low-level implementation classes, which makes code extremely rigid. Any small change in implementation forces changes in the business layer. With dependency inversion, instead of relying on concrete classes, both high-level and low-level modules depend on abstractions. This provides tremendous flexibility because implementations can change or evolve without disturbing the core system. The business layer becomes stable and protected, while implementation choices like databases, payment gateways, notification systems, or tax policies can be swapped anytime. Another major advantage is maintainability. Real-world enterprise systems live for years and constantly evolve. Requirements change, technologies get upgraded, frameworks become outdated, and business policies shift. Without DIP, systems become harder to maintain because everything is interconnected. One change breaks 10 other things. When dependency inversion is applied, code is organized around clear contracts and interfaces. If we want to replace Razorpay with Stripe, SQL with MongoDB, email with SMS, or one tax engine with another, we simply plug in a new implementation instead of modifying the core code. This significantly reduces maintenance overhead, effort, cost, and time. Dependency inversion also makes systems highly testable. When classes depend directly on concrete implementations like real databases, APIs, hardware services, or cloud resources, unit testing becomes painful. Developers require real environments, live credentials, or complex setups to run tests. But when systems depend on abstractions, mock or fake implementations can be easily injected. This allows developers to test business logic independently without external dependencies. Testing becomes faster, safer, cheaper, and more reliable. This is one of the biggest reasons enterprise architectures and frameworks like ASP.NET Core, Spring Boot, Angular, and Microservices heavily rely on DIP. Another strong advantage is scalability. When systems are built around abstractions rather than fixed implementations, it becomes easier to extend functionality. New modules, policies, providers, or services can be added without disturbing existing working functionality. Teams can also work in parallel more effectively. One team can work on business rules while another works on implementation, because both only depend on the abstraction contract. This leads to cleaner separation of responsibilities and supports modular, layered, and hexagonal architectures. Over time, such systems can adapt to business expansion, new technology adoption, and integration with external platforms far more smoothly than tightly coupled systems. Dependency inversion also supports better long-term design thinking. It encourages developers to think in terms of what needs to be done instead of how it will be done. This results in clearer architecture, more reusable components, consistent design standards, and a strong foundation for professional software engineering. Code readability improves because interfaces explain intent better than concrete class dependencies. Systems become more logical, predictable, and professionally structured. However, like any powerful principle, dependency inversion is not free from disadvantages. One major drawback is increased complexity, especially for beginners or small teams working on simple projects. Introducing abstractions, interfaces, dependency injection containers, and layered architecture may feel unnecessary when building small applications. For example, creating interfaces and decoupling every tiny class in a two-page project may actually overcomplicate it instead of simplifying it. Beginners may also struggle to grasp the concept initially because it requires architectural thinking rather than straightforward coding. Another disadvantage is the increased number of files, interfaces, and abstraction layers. Applying DIP strictly means introducing an interface or abstraction for almost every important dependency. This leads to more code, more structure, and sometimes extra mental overhead for understanding flow. When overused, it may lead to interface pollution, where hundreds of small abstractions exist, even for trivial behavior. This can make navigation and code exploration harder if not managed properly. Performance can also be slightly affected in some cases. Because systems depend on abstractions and often use dependency injection frameworks, there is an extra layer of indirection. Calls may go through interface proxies, containers resolve dependencies, and additional runtime lookups occur. Although this performance impact is usually minimal and negligible for most business systems, it may still matter in extremely high-performance or real-time environments. When performance needs to be ultra-optimized, developers must carefully decide where DIP is necessary and where direct implementation may be acceptable. Another disadvantage is that dependency inversion requires strong discipline and architectural understanding. If developers create poor abstractions, weakly designed interfaces, or inconsistent contracts, then the system may become more confusing than helpful. Abstractions must be meaningful, stable, and well-designed. If they are rushed or randomly created, the system will end up having too many unnecessary layers, duplicated logic, and unclear responsibilities. This can lead to maintenance pain instead of improvement. There is also the risk of over-engineering. Some developers apply DIP everywhere, even where it is not needed. For small projects, prototypes, student assignments, personal tools, or limited life applications, creating abstractions and dependency structures may waste time and effort. In such scenarios, simple direct coding might be faster, cleaner, and sufficient. Dependency inversion shines most in medium to large applications, enterprise systems, long-term projects, and environments where changes are frequent. In summary, the dependency inversion principle is incredibly powerful because it reduces tight coupling, improves maintainability, enhances testability, increases scalability, and supports clean architectural design. It protects business logic from frequent changes in implementation and ensures systems remain stable, flexible, and future-ready. However, it also introduces complexity, increases code size, may slightly impact performance, requires good design discipline, and can lead to over-engineering if blindly applied. The key is balance. Use DEP wisely where it brings real architectural value, especially in enterprise systems, financial systems, government applications, large products, and evolving software platforms. When applied thoughtfully, it transforms ordinary code into professional, scalable, and robust software architecture. Because systems depend on abstractions and often use dependency injection frameworks, there is an extra layer of indirection. Calls may go through interface proxies, containers resolve dependencies, and additional runtime lookups occur. Although this performance impact is usually minimal and negligible for most business systems, it may still matter in extremely high-performance or real-time environments. When performance needs to be ultra-optimized, developers must carefully decide where DIP is necessary and where direct implementation may be acceptable. Another disadvantage is that dependency inversion requires strong discipline and architectural understanding. If developers create poor abstractions, weakly designed interfaces, or inconsistent contracts, then the system may become more confusing than helpful. Abstractions must be meaningful, stable, and well-designed. If they are rushed or randomly created, the system will end up having too many unnecessary layers, duplicated logic, and unclear responsibilities. This can lead to maintenance pain instead of improvement. There is also the risk of over-engineering. Some developers apply DIP everywhere, even where it is not needed. For small projects, prototypes, student assignments, personal tools, or limited life applications, creating abstractions and dependency structures may waste time and effort. In such scenarios, simple direct coding might be faster, cleaner, and sufficient. Dependency inversion shines most in medium to large applications, enterprise systems, long-term projects, and environments where changes are frequent. In summary, the dependency inversion principle is incredibly powerful because it reduces tight coupling, improves maintainability, enhances testability, increases scalability, and supports clean architectural design. It protects business logic from frequent changes in implementation and ensures systems remain stable, flexible, and future-ready. However, it also introduces complexity, increases code size, may slightly impact performance, requires good design discipline, and can lead to over-engineering if blindly applied. The key is balance. Use DIP wisely where it brings real architectural value, especially in enterprise systems, financial systems, government applications, large products, and evolving software platforms. When applied thoughtfully, it transforms ordinary code into professional, scalable, and robust software architecture. In modern software development, microservice architecture has become one of the most popular and powerful architectural styles because it breaks large monolithic systems into smaller, independent, deployable services. Each microservice handles a dedicated business capability, such as authentication, payments, notifications, orders, users, or reporting. But even though microservices are independent units, they still need to communicate, share data, interact with external services, and follow business workflows. If microservices directly depend on each other's concrete implementations, technologies, or communication models, they become tightly coupled. This leads to fragile systems where changing one microservice breaks others, deployments become risky, upgrades become painful, and the entire purpose of microservice independence is lost. This is exactly where the dependency inversion principle plays a critical role in designing professional and stable microservice architectures. In a poorly designed microservice environment, one service directly depends on another service's exact endpoint, technology, protocol, or implementation. For example, a payment microservice might directly depend on notification. Microservices REST API structure or order service might tightly depend on inventory services database structure. Over time, if notification service changes its API contract, payment service breaks. If inventory service changes its underlying technology, order service fails. Such systems are microservices only in structure, but behave like a distributed monolith because they are tightly tied together. This is a classic violation of the dependency inversion principle in the microservices world, because high-level business services are directly depending on the low-level service implementations. Now imagine applying dependency inversion principle correctly in this scenario. DIP says that high-level modules should not depend on low-level modules. Both should depend on abstractions. In microservices, this means services should not depend directly on other services' concrete structures, implementations, or internal behaviors. Instead, they should depend on well-defined contracts, abstractions, and communication agreements. These abstractions may come in the form of API contracts, interface definitions, protocol schemas, message formats, or domain contracts. For example, instead of payment service directly depending on how notification service internally works, it depends on an abstract notification contract. such as an API specification, event structure, or interface specification. Notification service promises to follow this abstraction, and payment service trusts only the contract, not the implementation details. Now, even if notification service completely changes its internal logic, database, programming language, framework, or infrastructure, as long as it respects the abstraction, payment service remains safe and unaffected. Dependency inversion also plays a key role in microservice communication patterns. In traditional tightly coupled systems, services synchronously call each other all the time, leading to chain dependencies, latency issues, and cascading failures. With dependency inversion mindset, instead of directly depending on synchronous calls, microservices depend on messaging abstractions such as event buses, message brokers, or contract-first APIs. For example, instead of order service directly calling inventory service and waiting for a response, it may publish an order-placed event. Inventory service listens to the event and processes stock updates. The services now depend on event contracts rather than each other. This implementation follows dependency inversion because business logic relies on abstraction, event contract, not on direct service code. Another important area where DIP strengthens microservice architecture is maintainability and technology flexibility. Each microservice can use different tech stacks such as .NET, Java, Node, .js, Python, Go, or Rust. If they were directly dependent on each other's implementation, technology migration would become impossible. But with abstraction-based dependency, services can freely evolve internally while staying stable externally. This makes upgrading frameworks, updating databases, applying security policies, or refactoring internal design much safer and easier. DIP also improves testability in microservices. Testing a system where services directly depend on each other requires deploying multiple services together just to test a single module. This kills the advantage of microservices. But when services depend on abstractions rather than implementations, testing becomes extremely easy. Developers can use mock services, simulated APIs, contract testing, and stubs to validate behavior without needing real dependent services. This results in faster CI/CD pipelines, more reliable deployments, and higher confidence. Scalability is another massive benefit of DIP in microservices. If services are tightly coupled, scaling one forces scaling others, wasting cost and resources. But if they are independent through abstraction, each microservice scales independently based on its own load. For example, notification service, receiving millions of events daily, can scale horizontally without affecting payment service or order service. This results in optimal cloud cost, improved resilience, and strong fault isolation. However, dependency inversion in microservices must be applied wisely. Over-abstraction can introduce complexity. Too many contracts, unnecessary layers, or poorly designed interfaces can increase confusion. Therefore, abstractions must represent meaningful business behavior and stable agreements rather than unnecessary technical separation. The goal is not to blindly create layers, but to create logical independence that protects business stability and evolution. DIP also encourages event-driven, contract-first, interface-first thinking in microservices rather than service-to-service dependency thinking. It helps architects think from a business perspective, what behavior needs to happen, instead of which service should I call directly. This mindset differentiates professional microservice systems from poorly designed, distributed monoliths. When dependency inversion is applied consistently, microservices truly achieve the promised benefits: independent deployment, independent scalability, resilience, maintainability, and technological freedom. In simple words, the dependency inversion principle in microservice architecture ensures that microservices depend on stable abstractions, not fragile implementations. It protects the ecosystem from breaking when things change, enables continuous evolution, supports performance and scalability, and delivers truly decoupled, future-ready system design. It makes microservices stronger, smarter, and far more professional. The dependency inversion principle may sound like a programming guideline, but in reality, it is a powerful architectural philosophy. Whether you are building enterprise systems, financial platforms, government applications, or microservices, DIP teaches you to protect your core business logic from change. Technology, tools, services, and implementations will always evolve, but your business foundation should remain stable. When you build systems that depend on abstractions instead of concrete implementations, you gain flexibility, confidence, and long-term sustainability. DIP empowers teams to innovate without fear, upgrade without breaking, scale without limits, and maintain systems for years with clarity and control. In the world of microservices and modern architecture, dependency inversion is not just a good practice. It is a survival principle for building truly resilient and future-proof software. If you found this video helpful, make sure to like the video, subscribe to the channel, and share it with your developer friends. Drop your thoughts, doubts, or the next topic you want in the comments. I'd love to help you learn more. Thank you so much for watching. This is Vidaysketara channel, helping you become a smarter and stronger developer. See you in the next video. Until then, keep learning and keep coding.